So, that works.
Very good. Okay. Good afternoon, and welcome to the Simon's Electron Microscopy Center's Winter EM course. We're back. I have a voice. Glad to have a voice again. A couple items. Next week is going to be the start of a different modality. This is the last lecture in our EM fundamental series, and we're going to begin with tomography as the first modality of EM. So do watch. You received the EM handbook. Do watch the relevant lectures because that will definitely help feed forward and make the discussion and lecture a little bit more interactive. Hopefully it's not just a rote lecture. And the advantage of this is that if you come prepared, then you're going to meet experts that actually practice the modality we're talking about. We have people that practice tomography, FIP-SEM, crowd tomography, and it's going to be a little bit more impactful that if you come well versed in the subject, for you to pick your brain and understand how they actually apply that application to the science at hand. Okay, but as I said, today we're wrapping up our EM fundamental section, and this is one of the most important sections because all the topics today will feed forward for the relevant lectures later on. Because we are doing microscopy, optics, physics are important, but also understanding the limitations of our tool and how we can do some corrections and how we can set up experiments taking into account certain limitations. So today is on Fourier Transform and image formation. In previous iterations of the class, they used to be two separate lectures, but they're combined and very condensed. The hope is that you've watched Grant Jensen's lectures. Let's see how many actually have watched all this. How many hours? 6 hours? 1x, 2x? Great. Some of you actually do have watched that, and that will help. I mean, now, some of you are structural biologists. How many are actual structural biologists, X-ray crystallographers? So you understand Fourier transforms?
Yeah.
You do? You have some sense? Okay, so that's great because the hope here is we can augment some of that knowledge as well as spin it towards what are relevant information, what are the relevant concepts when we go into, let's say, single particle, like projection theorem, things like that. A lot of that deals with what we do is in Fourier space, a lot of that is in math that we might not actively have to think about it, but helps inform our experiments and helps make the whole technique a little bit easier and more practical to use. So the person that's really going to be doing the heavy lifting today is Lorenzo Finzi. He's a staff scientist here, and he's a relatively new staff member, but has quickly integrated in and is now learning a lot of the workflow here. He has had a previous life as an X-ray crystallographer, and then went to China and worked with Yi as a Cryo-EM person working on the spliceosome. So this is very common now these days that people span different fields. They've done X-ray crystallography in EM, or NMR in EM, or NMR in X-ray. And that's what you'll see quite readily here and in the center. Hopefully you can pick our brains and his brains and understanding and bridging that gap and really making use of the resources and information you already know and being able to focus that and apply it towards EM. So without further ado, Lorenzo.
Okay, thank you, Ed, for the nice introduction. So I want to start this lecture with a comic. Of course, on Fourier Transform. And so this is at the home of the Fourier Transform family, and you have a brother. I wish ScienceC would stop playing with that imaginary friend of his. Don't worry, it's just a phase he's going through. Okay, so just to, keep things light in this lecture, so I'm going to discuss Fourier Transform as well as image formation. So with Fourier Transform, I'm going to talk about sine waves just to briefly introduce them, talk about Fourier Decomposition, talk about some Nyquist, importance of Amplitude and Phase, Convolution, cross-correlation, and what kind of information we could actually get from Fourier Transform. And I will move forward and talk into image formation, talk about elastic and inelastic scattering, amplitude and phase contrast, the CTF, PCF, or PSF, talk about the effect of defocus on the contrast transfer function, and then I'll talk a little bit about estimation and correction. So as Ed mentioned, this is, I believe, 6 hours worth of video, so there's a lot of information. So I picked and choose some information that I thought, I wanted to cover and supplement. And so starting off with the sine wave, so sine waves have these three characteristics. You have the amplitude, you have the period, and you have the phase. And the relationship that it has with the circle is depicted in this animation. And I just want to point out that here you have 90 degrees, 180 degrees, 270, but you also have the radians of pi over 2, pi, and so on. And so just to show where that is on the sine wave, so you have the amplitude, so this amplitude would be 1. Here you have this period, and then you have the phase. Okay, so this is just a general sine wave. And so what happens when you make a change in the amplitude? So just to kind of remind us what happens when we change the amplitude in this sine wave. It goes from 1 to 2 in the amplitude. Whereas with the period, so 2 pi over b is equal to the period. Okay, so in this case, 2 pi over 1. Okay, so 2 pi over 1. And so when we change this to 2, it would be 2 pi over 2. So it would oscillate at a much faster rate. Okay, and then so here's our phase, which is depicted here. And one thing I want to point out with the phase is that although we have a phase of +1, it actually shifts in reverse. And here's a phase shift of 180 degrees, okay, which is relevant later on. Okay, so what is a Fourier transform? It could be considered a decomposition, right? So we have a complex wave. Okay, so a complex wave can be expressed into these different components. Okay, so that is important for what we're trying to do. And so what about Nyquist frequency? So Nyquist frequency is the highest spatial frequency that could be encoded in an image. Okay, so a waveform can only be decomposed into Fourier components as shown previously, with wavelengths that are at least 2x, 2 times the sampling rate, otherwise known as the pixel size. Okay, so that would mean if the pixel size is 2 angstroms, then the smallest sine wave that could be described has a wavelength twice that value, which is equal to 4 angstroms. So 1 over 4 angstroms is the Nyquist frequency.
So actually, crystallographers, what's your Nyquist limit? Your wavelength is highest resolution X-ray crystallography structure possible, theoretically.
So to try to answer that question in Fourier space, we could think about spots, right? We could think about the reflections, and when we look at those reflections, we look at the spot that goes out to the furthest edge, right? And so that could be where our highest resolution possible could be. Okay, so the famous ducks and cats of the Fourier transform world. And so if you have a duck and you get its Fourier transform, this is what you get. When you get a cat and you do the Fourier transform, this is the image that you get. Okay, so that's important to try to help us understand the significance of the phases and the amplitudes. Okay, so you have the amplitudes of the duck, but you have the phases from the cat. And you do the Fourier transform and you get the cat. Whereas you have the amplitudes of the cat and the phases from the duck. You do the Fourier transform of that and you can see the duck. So you can see in both cases the phases are the dominating factor in both images. Okay, so next we have convolution, cross correlation. So these are the two equations. So with convolution, it's an operation that can be considered the area of overlap between the function, which is f of x, and the spatially reversed function of the function h of x. Okay? So in the correlation, right here, operation, you have these two functions which are shifted and the area of overlap formed by integration, but this time without the spatial reversal involved in convolution. So that's how they're different. And so here's the convolution theorem, which relates the convolution between the real space domain to a multiplication domain in the Fourier domain. Okay, so that's some of the mathematics. Okay, so to try to understand that, Grant Jensen's lecture showed a duck. Okay, so you can also think of a protein in a unit cell. Okay, and the convolution with a lattice. Okay, so just like a crystal is made up of, many unit cells of proteins, and so your convolution would be the crystal, right? And so you combine these two functions, f of x and h of x, such that a copy of one function is placed at each point of the lattice, weighted by the value of the second function at the same point. What about cross-correlation? To try to understand cross-correlation, let's say you have a man and a house. Okay, that's our input image. And then you have this target image, which is just the man. So you combine these two functions, f and h, such that a copy of one function is placed at each point in space, weighted by the value of the second function at the same point. Okay, so you take an input image and a target image, then the correlation is formed by taking the shifted version of the target and placing it over the input image. So what does that mean? Okay, so here's our input image, here's our target. Okay, so you take this man here and you put it where the man is and you get this sharp peak, right? But you take this picture of the man and if you put it where the house is, you're just going to get a blob. Okay, so that's important for particle picking, for example. Okay, so different applications where we would use these functions. So applications for convolution describes point spread function, which we'll talk about later, contrast transfer function, which we also will talk about later. But so cross correlation is important for particle picking and also the alignment of our micrographs. So that's why it's important for us to try to understand these sometimes complex mathematics. Okay, so what types of information can we actually get from Fourier Transform? Okay, so here's a micrograph of a protein sample here at NYSBC. And in Fourier space, we have the power spectrum of that same micrograph. And so what you can see is these concentric rings, okay? And so this distance is 100 nanometers, but in Fourier space, so we have our low resolution details towards the center of the ring. So as you start coming outside, you get to higher resolution. And it's the same thing in X-ray crystallography. So when you see rings coming out further, you can see the higher resolution details. Okay, so this sample has some crystalline ice. So same protein, same data set, maybe different parts of the grid. And you can see this at 4 angstrom is a ice ring, which also, if you're an X-ray crystallographer, you can identify. And so these are types of things that we look at when we're looking at our data sets. When we have our time on the microscope and we look at our images, sometimes we can, try to look at our images and try to think about, what's the density of our molecule. But we can also look in Fourier space and we could try to understand what type of information it can tell us. This is the diffraction of the ice ring. This is how good these concentric rings look. Okay, so that.
Clear about that water ring, why the first one and second one may or may not be good, or may be fine, because you're going to see that quite often. You can take a power spectrum of your micrograph, and you see a water ring. that does not mean an image is bad. You might have crystalline ice, and you will see discrete diffraction. You might have ordered ice and discrete diffraction points, but that does not also mean that the image is bad. What that is indicating is that you have some order. If you have the very, very thick buffer, we were mentioning a couple lectures back about sample prep. Let's say your particle of interest, your molecule of interest, is huge, and you need half a micron support film to sustain it. That water ring is your buffer, will be more apparent. Okay, so I want to point that out. So there's a lot of useful information in that power structure that Lorenzo just showed you, and by eye, there's a lot of information we can unpack. So I'm just giving you another applied application. So was that clear? Water ring is at what angstrom? Lorenzo's at 4. It's a good enough estimation. It's 3.46 or 8. It depends on how ordered and what order forms of water. So there's like crystalline,
Amorphous.
there's amorphous, there's multiple forms of water that has order, and hexagonal ice is very clear. That's very sharp. You see that sharply. But there are other forms of ordered ice. I'm going to point that out because we see that a lot, and you're going to see that quite often, especially when you go to the microscope. But to put in context why this is tying in a lot that we've just mentioned, because it pulls in a lot of information, and this gives you great diagnostic criteria to gauge reasonable images or improvement of sample.
Yeah. So these are examples of applications which we would use Fourier space to try to understand what's going on with our samples. Okay, so now we're going to talk about image formation. Okay, so first of all, let's talk about the duality of the electron. So we have an electron which, sometimes can act like a particle, sometimes can act like a wave. And so electrons are negatively charged particles. They interact with other particles elastically and inelastically. An electron wave is almost a plane wave diffracted by atoms and determined by atomic scattering factor Z. Okay, so to try to understand this a little bit in more detail, so electrons have 3 types of interactions. Okay, so firstly you have your non-interacting electron, which basically just goes through and doesn't interact with anything. And then you have this elastic scattering electron. Okay, so you get the deflection by the electron cloud, and it maintains its energy. You also have inelastic scattering. Okay, so you have 2 types of inelastic scattering. You have this collision with the nuclei produces radiation. And then you have collision with beam electrons, which also produces radiation. Okay, so it's important to try to understand the different types of interactions that the electrons are having. So, what about X-rays? So X-rays are scattered by the electrons in the specimen. The sample electrons oscillate with the period of the incoming X-ray wave, and the electrons are scattered by the electromagnetic field. I think Grant Jansen talked a little bit about the differences in terms of X-ray, when an X-ray is shot. And so I think this is a great image that shows the difference in EM versus X-ray. So one of the major differences with EM versus X-ray crystallography is EM has a lens which can focus the electrons. With X-ray crystallography, there is no lens. And so because of that, we lose the phases, okay? And so, yeah, this basically just shows, this is the lens. So you have your Fourier Transform, and then you have the inverse Fourier Transform. This is the back focal plane. And then, so you have your X-rays which hit this specimen, and you have this diffraction. Okay, so we lose the phases, so we have to use other methods to obtain those phases in X-ray crystallography. Okay, so the next topic is trying to understand the difference between specimen, amplitude, and phase contrast. Okay, so we talked about how the electrons are scattered. So now we'll talk about the specimen itself. These are 2 different ways the specimen interacts. Okay, so you have this amplitude contrast, you have this phase contrast. This comes from the specimen. Okay, so the difference is that in amplitude, some parts can be electron transparent while the rest is not. Whereas in phase contrast, the objects are electron transparent. Okay, another difference, contrast is produced because of differences in the mass or thickness, that Z, which I mentioned earlier. Okay, whereas phase contrast is produced because of the differences in the phases of the scattered electrons compared to the unscattered. Okay, so Grant Jensen, the way he described this in his lecture to try to understand this, he used that duality of the electron. So in the case where the electron acts as a particle, it's easier to understand amplitude contrast. Whereas where it acts as a wave, it's easier to try to understand the phase contrast. And so, so in amplitude contrast, the transmitted electrons produce an image, right? And so this is basically a specimen which shows the waves which are coming in. And so thicker regions produce more scattering. And so in cryo-EM, the amount of amplitude contrast is present, but it's extremely low. Okay, especially for cryo-EM, 7%. And in phase contrast, okay, so you have this interference, right? So you have these two positive waves which constructively interfere and produce larger waves, right? Whereas you have these two waves here which interact in a destructive fashion, okay, and cancel each other out. And so phase contrast, the scattered and the unscattered electrons do not have the same phase. Okay, so you have the non-scattered and you have the scattered. So these two types of electrons don't have the same phase. Their interference produces differences in intensity. And so thin biological specimens have phase contrast. Okay, so we treat them as phase objects. And I believe Grant Jensen used the example with the wave throwing a stone into the lake and seeing the ripple effect of the waves. Okay, so what about wave propagation and the phase contrast? So we have our specimen, okay? And so Grant Jensen used this example of an orchestra. Okay, so you have the beam which comes down and doesn't interact at all, right? So 0 degrees. So this is the Argand diagram. Okay, so in Grant's lecture, he talked about the phase shift coming from two places, right? One was the path length. The second was a 90-degree shift. Okay, so all these phases have the 90-degree shift on top of the path length. So what I'm showing here is I'm talking about the degree path length. So here would be 0. Okay, so it's just, this is the Argand diagram. This is the sum. And so you have 90 degrees would be the blue. So this is the sample, this is the lens, and this is the image plane. And this is just an image showing you the propagation of waves at these different angles. Okay, so they, as mentioned earlier, have different phase shift because they have different path lengths. Okay, so if you plot that, if you plot each of those waves as a function of spatial frequency, okay, this is what you get. This is their summation. Okay, so this is the orchestra example that Grant Jensen talked about, where if you have the symphony, right, you have, in a symphony you have high instruments, you have low instruments, you have medium instruments. So let's say you have a cello, okay, maybe a cello and a violin and a bass. Okay, so low, medium, and high. So if you put microphones at these instruments, they will make sound. If you take away the microphones, you will take them away. Contrast transfer function is just like that. Okay, so when you plot this over spatial frequency, right, so here's our first wave, here's our second wave, here's our third, here's our fourth, here's our fifth. And then when you plot that, so this maximum information comes from here. Okay, so they have microphones and they're very loud, right? But so here is zero information. Okay, so we lose that information. They take away the microphones and you can't hear them. Okay, and so this would be partial information. Okay, so the contrast transfer function is an oscillatory function that describes how contrast or information is transferred to the image in terms of spatial frequency. And each frequency component represents information. So we have this low frequency here is the lower resolution, where we have the high frequency representing the higher resolution. Okay, is that clear for everybody? Okay, so that leads us into the point spread function. And so let's say you take an object, let's say you take a gold bead and you image it. The point spread function basically accounts for the blurring. And so it represents the aberrations in the microscope. In Cryo-EM, images are blurred by the convolution with the point spread function arising for a detector as well as imperfections in the imaging system. Convolution of the object, Fourier Transform with the point spread function generates image imperfections. And to try to explain that a little bit differently, so again, we have our object, okay? We have different objects. And these are the different images which were blurred by point spread function. Okay, so you can see how the image is blurred from the object. So the point spread function is the Fourier transform of the contrast transfer function. And the image is equal to the object convolved with the PSF. So these are relationships that exist between the point spread function, the contrast transfer function, and they try to help us understand what image we're looking at. Okay, so what about the contrast transfer function? So this is the mathematical representation of the contrast transfer function. And it describes how aberrations in the microscope modify the image of the sample. And it depends on several parameters. One of them is this spherical aberration, otherwise known as CS, whereas the second would be the defocus. Okay, it's also affected by the aperture, but so I'm going to focus a little bit on the defocus. So what effects of the focus, what effects do focus have on the contrast transfer function? Okay, so as I showed you earlier, here's the lens, here's the sample, here is the beam coming in at different angles. And you know, I mentioned earlier that we have the contrast transfer function, which is you have these different angles coming in, and those waves contribute to the contrast transfer function differently based on their path length, right, as well as their phase shift. And so these three states of the microscope, you have this over focus state, and under focus. And to apply the defocus, you reduce the strength of the lens by reducing the current, which changes this angle. Okay? So these three states of the microscope. So by changing the defocus, the path lengths of all the waves will be changed at the image plane. This is the image plane. And if you also will remember Grant Jansen's lecture, he also talks about how this image plane actually changes depending on which focused state you're in. So you're changing this angle, but you're also changing the plane. And the wave functions at the image plane will be different. That's what I just said. So certain waves which were not detected earlier will now be detected, and vice versa. By applying a range of defocus, information lost at zeros can be retrieved. So I'm going to say that again. By applying a range of defocus, information lost at zeros can be retrieved. Okay, and so I'm going, yeah?
So before we can talk about the destructive waves that cause that loss of energy, is that caused by the aberrating selection?
So wait, just to understand your question, so you're asking if this, so this nature right here of the wave is caused by the scattering from the specimen, right?
That would be there if you had a perfect microscope. That's just the way that the waves are going to interact. Some of them are going to interfere constructively, and you'll get that information out, and some will be destructive, and will zero out, and you won't get information at that resolution.
Right, so I talked about the electrons interacting with the specimen, right? And then I talk about how the electrons propagate. So depending on their interaction, either inelastic, elastic, or the third type was, no interaction. Depending on those interactions, every electron will have a different interaction with the specimen and will produce a phase shift as well as the path length difference. Okay, is that clear?
So going back to the last point that you repeated,
Mhm.
so we, when you collect cryo-EM single particle data, you usually collect your data across a range of defocuses. So, -1 to -2, and that's so you can retrieve all of those zeros that you lose. But inherently, some people actually, instead of just doing a defocus range, they just set 1. And it's always going to be a function of how well you find zero focus. So this is practically very applicable in case you ever forget to set a defocus range when you set up automation and you walk away from your scope. There's always going to be an inherent defocus range just in your sample itself. Like your ice is a little bit thicker or thinner, like the carbon support has a little bit of, a bend in it or whatever. So, but yeah, that's what you're trying to get. That's why you do a defocus range instead of one nominal defocus value.
You mentioned the aberrations of those. Well, the aberrations all contribute to this. Defocus is an aberration. Spherical aberration, theatrical aberration. There's astigmatism, which is defocus corrections, and then there are high order
And then, when you do that defocus, is that does it happen during the single image taking, or does it happen over a series of images?
So
if you're going through the rain, are you going through sort of one image, changing the focus,
So-
changing the focus?
You change it basically every image.
Okay, every image. Okay.
And you give the software some range and tell it to go, and each image it'll pick a different defocus value.
And then
Yeah.
CTF estimation software like CTF Find will calculate the actual defocus value. So this is just what the microscope thinks is -2, but it might be -2.2 or whatever.
Which is why some people just set one
value.
focus value or one defocus value, and then assume that imperfections in the microscope or the stage or the specimen
grid,
itself
yeah, exactly.
are going to vary it just sort of naturally, so you'll cover enough of that CTF, you'll switch that CTF and you'll recover the information that you need. But usually you get a range, because that's, and there are other uses of that we can talk about.
yeah, and so here we have some images of carbon, and here is their defocus values and their tone rings of the second image. So here's the first image, here's the second image. And so if you can notice the second image, the tone rings are located closer to the origin, okay, and they oscillate more rapidly, and you can see that in the contrast transfer function. So when you look at the contrast transfer function, I want you to try to always think about this. So you think about, okay, so here's the maximum values for these frequencies, here's the zero information, and then here's, you know, this partial information. Okay, so you can think of that here as well. Okay, so this is just showing the two different defocuses. But so if you're actually looking at a micrograph with particles, so here's a negative stain at negative 0.6 micron defocus. And as you can see, as you go to the right, you shift to more negative, and your contrast gets higher. Okay, so negative stain electron micrographs had different defocus, and this is their corresponding power spectra. And so the micrograph 1 is set closest to defocus, followed by sequentially higher defocus. So these are the types of effects that defocus has on the contrast transfer function. And this is actually what we're looking at images in the micrograph. But again, to touch on negative defocus, so why do we use negative defocus? Why is it something that we do to see our images? Is it, you know...
And by negative defocus, you mean underfocusing versus overfocusing.
Right. Right. And so here, based on this image, you know, you can say that the contrast looks better. So if you go back to 1971 and you look at the seminal paper by Klug, so they measured the measurement and compensation of defocusing and aberrations by Fourier processing. So they basically said that underfocusing will be advantageous as there is a contrast increase over the entire transform and relative enhancement in the high resolution components with respect to the lower. This is why we underfocus. Okay, and to actually go into the paper, and so these are 3 different focusing CTF. And so at the top you have in focus, and so I want you to think about the spatial frequency. So this is low spatial frequency and this is high spatial frequency. Okay, so if you notice here, you have no contribution from the contrast transfer function at this in focused image. No contribution at all. And so when
no low resolution information in that upper
right.
CTF.
So no low resolution information. Okay, so when we do 90 nanometer underfocus, we get the high resolution components begin to contribute no high resolution artifacts. Okay, so you can see that this portion of the CTF changes. Okay, so then you might ask, oh well, why don't we just shoot it up and do, you know, this 500 nanometer underfocus? When one wants to obtain a high contrast image of details in this medium resolution range and is not concerned about artifacts at higher resolution. So there's artifacts contributed to this. So there's a balance, okay? So you don't want to over-focus, you don't want to under-focus too much. There's a balance, and you have to figure out what that is. And so for us, let's say we use, I believe...
-1 to -2 is like a good...
-1 to -2 is a good range.
And right here, that is like half a micron right there, right? So this is not like a hugely defocused image right here. So you get nice space, like a broad coverage of all your spatial frequencies right here.
You notice that the high resolution is as you're under focus, the winging gets faster and faster. And so when you're really highly under focus, like 2 microns or 3 microns or something like that, it gets so fast that if your CTF estimation is off by even a little bit, the phases will be out by 90 degrees, and then beyond there it's just wrong. So the advantage of doing low under focus is it doesn't oscillate as fast when you're doing high.
At the higher spatial frequencies, yeah.
Any questions about this? Okay, so going back to what we talked about earlier, so this is a great review. And so we have this contrast transfer function at different defocuses. And again, I want to go back and think about, okay, so this is the max here information, right? At the point where it hits the spatial frequency of 0, right? We get the 0 information right here, and right here. So the question, right? So when you see the contrast transfer function, you could think about that. You could think about the orchestra. And so a data set should comprise images with an adequate range of defocus levels. Okay, so that's why, again, to hit home, we do a range of defocus so that we can try to recover information in the 0 zones. And you can try to image this contrast transfer function and see how that might be possible. And so this Siemens star, it's a graphical object with a continuous decrease in the spacings. And this is just to show you an example of the difference between in focus and defocus. So again, the points that I want to hit home are that we use defocus as well as we want a range. And so how do we estimate the CTF? So we've collected a data set with our microscope, and maybe some people will use a defined defocus, but maybe they've used a range of defocus. But so when they have their data set, how do they actually go through and figure out which defoci was used at on every micrograph? And so the defocus is estimated by comparing the theoretical CTF curves at different defocus against the experimental power spectrum. So this is CTF Find. There's a handful of software that you can use to estimate your CTF. Normally we do that as we collect our data. And so the experimental power spectrum must have clearly identifiable tone rates, right? For the accurate determination of your defocus.
So this is what Bill was talking about, but now looking at an actual 2D power spectrum. The further you go out to the edge of those images, you can see those rings start to disappear. They start oscillating faster and faster, and then just become sort of indistinguishable. And it drops off.
And so with CTF estimation, you also have to take in to consideration astigmatism, and it requires the determination of the minimum and maximum defocus directions of the angle. That way you can determine the astigmatism. So this is why we try to align the microscope and minimize any kind of astigmatism that you guys might have before we collect your data.
And if you want to take part in our practicals that we have for this course, where I'm going to be doing a microscope alignment practical where we're actually be going through and tweaking astigmatism. So you'll get to see an astigmatic electron beam and what knobs and buttons you have to push to make it astigmatic.
I have 2 questions. If you do per image CTF correction, why do you need to collect images at different defocus values? Like you were saying earlier.
Yeah,
Wait,
CTF estimation is just, again, coming up, trying to figure out what the CTF is for that particular image. You don't recover information that's not there by doing CTF estimation. So you do the range of defocus values so that you can sort of fill out the CTF, because you're going to take all of your particles, right, and each one of those is going to come from a micrograph with a certain CTF. So certain frequency information is going to be missing from that single particle in your image. So you combine all of them to try to get your 3D structure. You want to have information at all of the resolutions possible.
Okay. And then when you're doing this CTF fit, could it be like beneficial to low pass filter it so that it's not miscorrecting the high resolution frequencies when it's going up in like they were saying?
So it does that. Just judge based on the theoretical experimental.
I mean, there's going to be,
Like when
so each program is going to basically spit out some sort of like confidence interval. It's going to be like, okay, at this resolution, I am like this % confident of what the CTF is, and that will sort of tail off. So it'll, I mean,
You tell it also, you
And
give it
you'll-
a resolution range to search for.
Yeah,
You give it
to
a low
consider.
resolution cutoff and a high resolution cutoff.
Right.
And it fits only between those values.
So it's a
And
sort
it may
of-
fit better than that.
yeah.
If
Alright.
it searches in a certain region, within a certain part of the spectrum.
Any other questions?
And it'll give you, and this is a good point, this lecture is very dense. The videos themselves are fantastic, but also very dense. So to try to give it more practical application, you do the CTF fit, and it'll give you a resolution for your image. Basically, so you've got tone rings out to about this far. You've got information to this resolution in your micrograph. And you can actually sort by that resolution. So if you're going on to do your 3D reconstruction, you might want to ignore images that only have information out to 12 angstroms if you're going for something really like nice, near atomic. So understanding what that means will sort of help you filter out certain micrographs by looking for, tone rings that correspond to ice, and by going through and looking at your CTF estimation and seeing what resolution information you have in each micrograph.
When you're doing image collection, you're doing a range of different focus values. Does it always proceed in the same order so that you aren't biasing?
So, I
Which-
think the different programs probably do it differently.
They all have different algorithms.
Software we use called Electron, it does a random, it uses a Python random number generator to
To
choose.
say, between these values that you've given me, I'm going to randomly pick one for each of them.
Perfect, great.
And you can also sort based on the focus value. All of that metadata is sort of tied to the image, so you can get rid of images that have certain focus values.
But I think EPU, actually, FEI EPU software, you give it 3 or 4 values or a range of values, and it does step through those values. But we don't use that.
Anything else?
So one thing, I don't know if it's been covered yet, but when you're looking at that image right here on the upper right hand side, what you want to see for a good CTF, like the product of that software is you want
Maybe
go
stay
back.
there.
Yeah, right there. Yeah, you want to see that the experimental data is fitting the theoretical. So sometimes you'll see that all of the zeros are off. It means that software did not find those zeros for you. So those are the types of micrographs you want to either reprocess or just exclude because it didn't measure your CTF correctly. So you can do sort of like a qualitative, like assessment of your data that way.
Okay, so that's how you estimate the CTF. Okay, so after the accurate measurement of the defocus levels in the image, the contrast reversals associated with the CTF can be corrected by phase flipping 180 degrees. Okay, so we flip the phases. So we estimate CTF and then we correct. So the program normally does both, right? And so this will not affect the amplitudes. These are better corrected later in processing. But these if you remember going back, those 0 points of information, which are here, right? If you flip, those still remain, right? And so you lose those, right? Even if you do the flipping. And so that's why, again, we use the range of defocus to try to get different zeros. Okay, is that clear? Yeah, okay, thank you guys.
That's it.
Yeah, that's
Nice.
it. Any other questions?
Yeah, we've got 40 minutes left, so I know this was a dense one. If you guys have any questions about any of this, or really anything else, there are at least a few people in this room who know what they're talking about, mostly Bill. So ask Bill.
Yeah. Okay.
Is everybody signed in to make sure we have accurate attendance?
Yeah.
Yeah, you guys were late.
We were here on time. I just went with that.
And we, Youngzy and I are going to finalize the list of people who are interested in the journal club and the practicals, and I guess to what degree. So let me know, or like write it on the sheet, I guess. That would actually probably be nice, so I have it associated with your names, because I don't know everybody's names yet. And then we are going to start picking articles, and I think the first practical is next week.
Wednesday, yes.
Next Wednesday.
Yep.
And that is
So-
going to be our microscopy practical, so we're going to go over microscope alignment, mostly the gun and the condenser systems. So you can fill in with microscopes a little bit.
So next week, Monday, is going to be tomography, and that's with Wei Dai from Rutgers, so that should be pretty interesting for a lot of you guys. And then the Wednesday after that is going to be the practical.
Yeah.
And all of this will be done here.
Yeah, for the practical, we'll meet in here, and then we're going to go down to,
12, T12, right there.
oh, we're going to go to the T12.
Yeah.
Even better. So we'll just walk right over here to the T12. So I guess just a show of hands, who's interested in journal clubs and or, let's say, both. If you're interested in both the journal club and the practicals. 1, 2, 3, 4, 5 is good.
Yeah.
Anybody interested in like just the practicals? Okay. So that's
4.
So that's 9 total. Cool.
That's good. That's a good number.
Yeah, it's a good number. Well, T12 can probably accommodate everybody.
Oh, yeah.
Yeah.
Definitely.
With 9 people, I don't know how much time, like actually hands-on time on the microscope you guys will get, but these kind of alignments aren't things you'll actually have to do as users of a center like this. These are the kind of things that like Laura does before or during your session if things are misaligned. But then all of the practicals after this, which are mostly going to be data processing, so there's going to be 2 tomography practicals, 2 single particle practicals, and one of those single particle